Namaste students. In today's lecture, we are going to discuss one of the most important nuclear reactions in the field of nuclear astrophysics. As I have been telling many times in the lectures, it is the nuclear reaction which is the reason for evolution of universe and synthesis of elements since the Big Bang, say 14.7 billion years ago. And as part of recap, let me quickly inform you what I have discussed in the previous lectures. In PP chain and in CNO cycle, I have shown a few nuclear reactions which are responsible for the synthesis of various elements, isotopes, isobars and isotones. So, various nucleides we have seen in the synthesis of elements. What is the role of PP chain and CNO cycle? And we have seen that it is the burning of hydrogen which is playing very important role. What will happen after hydrogen is exhausted? What is the ash of hydrogen burning? What is the ash of hydrogen burning? And how it plays important role in the creation of carbon 12 nucleus? That we are going to discuss in today's lecture. All right. Please recollect what did we learn from HR diagram. HR diagram. Please recollect the location of white dwarfs, location of main sequence stars, location of red giants, super red giants. So, I am sure you will remember when I say that, if I say that super red giants have not yet been discussed, and in today's lecture I am going to correlate the synthesis of carbon 12 with super red giants, all right, and how helium burning is playing role in the synthesis of this carbon 12 and also in the formation and evolution of super red giants, all right. Then the nuclear reaction which is responsible for the creation of carbon 12, that is called as triple alpha process, one of the beautiful nuclear reactions which takes place inside the star. Not double alpha process, it is a triple alpha process, and this kind of wording you will never come across in this course. This is the only place where you will come across triple, some particle and then some process. So, this triple alpha process is going to answer one of the important questions which I have posed in the initial lectures, that is stability gaps. What do you mean by stability gaps? Do you remember? Mass number 5 and mass number 8, right? A is equal to 5 and A is equal to 8. These are termed as stability gaps. By maintaining these gaps, how elements are formed? It was a big question for the researchers. On one hand, we are able to see the elements in the universe. On the other hand, we are seeing the gaps at A is equal to 5 and A is equal to 8. What is the answer for this stability gaps? Who is bridging the stability gaps? That we are going to understand in today's lecture. So, you can imagine the importance of today's lecture when compared to all other lectures. So, it is not only informative, but also it is a classical example of nuclear physics fundamentals, how they have played role in understanding the synthesis of elements and the evolution of universe finally. So, it requires more attention from your side, all right. Now, like many nucleides, can carbon 12 can it be formed due to helium burning in normal state? Can it be formed in the ground state or not? That we will check. So, in today's lecture I am posing some questions and some points, so that you can get some idea about today's lecture, what are the points I am going to cover, all right. And already I have discussed the concept of non-resonant reaction when they are induced by charged particles, and resonant reactions induced by charged particles. And in today's lecture, I am going to take the help of charged particle induced resonant reaction in understanding the formation of carbon 12. So, overall lecture is centered upon the creation of carbon 12, all right. Then whether this nuclear reactions which are leading to the formation of carbon 12 be done in the laboratory using direct techniques or indirect techniques? If we cannot do using direct technique, what is the reason? And what are those indirect measurements by which we can perform any reaction for the synthesis of carbon 12. So, let us see how these points can be covered and what are the answers for some of the questions present in the slide. Let us start. So, in the helium burning, you have to understand that once hydrogen gets completed, once hydrogen is exhausted in the star, what is the ash of the hydrogen burning? It is a helium, right. So, it is quite natural that once hydrogen is exhausted, the contraction of the helium core starts. So, helium starts burning. Helium starts burning when hydrogen is exhausted, and at the core when helium starts contracting, what will happen? You can easily imagine there will be increase in the density, there will be increase in the temperature. It will continue, but interestingly, as the helium core contraction happens, around the helium core, what will happen? Whatever shell is present around the core, in that shell hydrogen starts burning. So, remember, I am doing a very clear distinction. At the center of the core, helium starts burning. What is the consequence of this helium burning, that we will see soon, but the contraction of the helium core leads to the increase in the temperature and the density. Around the core, what will happen? For example, if this is the core and if this is the shell, okay, around the core, in this shell hydrogen burning starts taking place. And with time, if you see, expansion of the outer regions of the star happens in such a manner that many a times it will be like 50 times larger than the original radius. I am talking about the radius of the shell, and this shell contains the hydrogen, and the burning of hydrogen is causing the expansion of the outer shell, where the central core, in the central core helium burning is taking place. All right. So, now these two are happening simultaneously. On one hand, because of the high temperature at the central core in which helium is burning, the shell around the core starts expanding. So, the size is becoming big and much bigger. Because of this, the star is considered as giant star. Now, where from this red is coming? See, the contraction of the helium core and the expansion is happening in such a way that after a certain time the surface starts cooling, the temperature of the surface falls down till the wavelength enters into the red region. So, because of the shifting of the wavelength into the red color and because of the outer expansion of the core in a big size, we call this star as super red giant star. So, it is a contraction of the helium at the core and expansion of the hydrogen in the shell around the core, which is responsible for the formation of red giant and then super red giant. So, this is how the formation of red giant and super red giant takes place inside the star. Remember, hydrogen is exhausted at the core and it is a helium which is burning. So, it is quite natural to expect. So, because of this burning of helium, what will happen? What kind of elements are formed, okay, and how it helps us to understand the creation of carbon 12, that is what we are going to discuss in today's lecture. All right. Now, people have thought that if there is a stability gap at A is equal to 5 and A is equal to 8, then when alpha particles are burning within the core, so it is the alpha plus alpha leading to the formation of beryllium 8, which is happening inside the core, right. And there is always a very less probability that third alpha can also participate in the reaction. And if this triple alpha process happens, if at all it happens, then we can expect the formation of carbon 12, right. So, this is how synthesis of carbon 12 can be understood, but things are not so easy. How it happens? Is it a single step? Is it a double step? Is it a triple step? That we will discuss. Okay. Why only carbon 12 formation should happen? Once carbon 12 is formed, you have the plenty of helium in the core. So, alpha plus carbon should lead to the formation of oxygen 16, and alpha plus oxygen 16 should lead to the formation of neon 20. Neon 20 plus alpha should give rise to Mg 24. Mg 24 plus alpha should give rise to silicon 28. All these elements are supposed to be synthesized just because of alpha capture. Why we are discussing alpha capture? Because it is the helium is the ash of hydrogen burning, and in the core you have helium. Only helium? Yes, 98 to 99% helium is there. Remaining I will discuss later what is happening to the remaining percentage by mass. Okay. So, because the majority of the star's core is helium, we can always expect alpha capture reactions to take place continuously, But whether all these elements are formed in reality? No. The formation of the elements stops with the oxygen 16 only. It will not go further. There is a beautiful physics reason behind it that we will discuss. But before that, we need to understand the nuclear reactions and physics behind it for the formation of carbon 12. All right. So, let us see how carbon 12 is formed with this background. As I said, when people were thinking how these stability gaps are bridged, okay, how these gaps are bridged. People have given a lot of thought to this question, how to bridge the stability gaps, mass gaps. When it was clear that once hydrogen is exhausted, it is the helium at the core, maybe alpha plus alpha is giving rise to beryllium 8 and alpha plus beryllium 8 is giving rise to the formation of carbon 12. For this, there is no need to have any element or any nucleus with mass number 5 and 8. So, this is a thought, and Salpeter, the researcher who proposed this creation of 12 carbon as 2-step process. Okay. Carbon 12 actually it is happening via 2-step process. All right. So, what is this 2-step? First, alpha plus alpha is giving rise to beryllium 8 in the ground state, But the problem is its lifetime is of the order of 10 to the power of minus 16 seconds, you see. So, what can you expect? Once alpha and alpha undergoes fusion with each other, beryllium 8 is formed and it quickly goes back to the 2 alpha particles. So, you can expect some kind of equilibrium between 2 alpha particles and beryllium 8, very less lifetime, 10 to the power of minus 16 seconds. Now, on one hand I am saying carbon 12 can be formed because of this process, but on the other hand you see that I am saying alpha plus alpha is giving rise to beryllium 8 and it is quickly coming back to 2 alpha particles. So, where is the question of carbon 12 formation? So, that is where the interesting aspect is. Before that, please do simple calculation. You know how to do binding energy per nucleon calculation, right? For alpha, you know it is 7073 keV, and for beryllium 8 it is 7062.44 keV. All right. If you do this, once alpha plus alpha reacts with each other, you can see that beryllium 8 in this level scheme, if you see, it is 922 keV above the alpha plus alpha threshold. It is 922 keV above the alpha plus alpha threshold. All right. It is very less. See, things are happening very naturally, and how this less difference between alpha plus alpha threshold and barium 8 is going to help us in a tremendous manner to understand the synthesis of carbon 12 and the evolution of the universe. I am highlighting this sentence. Please remember, very less mass difference between alpha plus alpha threshold and the ground state of beryllium 8. All right. So, as I said, once beryllium 8 is formed, it quickly goes back to the alpha plus alpha, and once again alpha plus alpha gives rise to beryllium 8. So, there will be an equilibrium, there will be an equilibrium. Now, if you calculate the gamma energy for this alpha plus alpha Eg, alright. Do you remember it is basically B square, is nothing but gamma energy, and if you have gamma energy, it becomes easy for us to calculate the centroid of the gamma peak. Why I am using the word gamma peak? Because these two are charged particles. Had it been induced by some non-charged particle like neutrons, there is no point in discussing about the gamma peak, isn't it? So, alpha plus alpha reaction, what is its gamma energy? It is about 31.4 MeV. Please remember the value. And by substituting this gamma energy into the formula of centroid of the gamma peak, centroid of gamma peak, this formula you can get easily in terms of temperature, say T8, if you can take T8. Now, what is the meaning of this centroid of the gamma peak? It means if the temperature is above 10 to the power of 8 kelvins, if the temperature is above 10 to the power of 8 kelvins, then there is a possibility that fusion can happen. So, when there is a possibility for the fusion between alpha and alpha can happen, when the temperature region is above 10 to the power of 8 kelvins. See, why I am highlighting this? Because this is the temperature region in which alpha plus alpha reaction is taking place. There are regions where even at 10 to the power of 7, 10 to the power of 8 and much below that, synthesis of many elements take place, and sometimes you may have to go for 10 to the power of 10 kelvins. So, as part of this course you need to know the temperature region during which type of nucleus is formed, which kind of new elements are getting synthesized, those things you have to understand. So, in this slide I am clearly discussing how to find out the temperature region corresponding to which the beryllium-8 is getting formed, okay? And this certainly helps us in understanding the synthesis of carbon 12, all right. Now, we have understood that beryllium-8 is formed because of the alpha plus alpha, and beryllium-8 is having lifetime about 10 to the power of minus 16 seconds. Now, if you consider in that temperature range, the transit time between the alpha particles is about 10 to the power of minus 19 seconds. 10 to the power of minus 19 seconds is transit time of alpha particles, So, before beryllium-8 goes back to the 2 alpha particles, there is a probability that beryllium-8 can capture alpha again. See, this is the turning point in the formation of carbon 12, and this is the second step. What is the first step? Fusion of 2 alpha particles giving rise to beryllium-8, and beryllium-8 capturing the alpha particle giving rise to carbon 12. And this carbon 12, you can see the level scheme here. Ground state, first excited state about 4.4 MeV is the energy, and second excited state, if you see, it is 7.644 MeV. Carbon 12 second excited state is 7.644 MeV. Remember, this state is not very easy to measure. What is the reason? I will discuss now. So, I have shown you how 2 steps are playing role in the formation of carbon 12, all right. And if you do the simple calculation, alpha plus beryllium, okay, the Q value is about 7.366 MeV, 7.366 MeV. So, what is so specialty about it? When people have tried to understand the abundance of elements which people have measured from the observations, it is not in agreement with the theoretical predictions if the formation of excited state carbon 12 happens in a normal way, So, there is a mismatch. Then Hoyle has given a beautiful theoretical suggestion for which he won the Nobel Prize. So, Hoyle has suggested no issue, we can always get agreement between the theoretically calculated abundance of carbon 12 and experimentally measured carbon 12 abundance, provided the carbon 12 nucleus which is formed because of the alpha plus beryllium 8 is formed in the excited state through a resonance mechanism, and the interesting part is that its spin and parity, if you see, it is 0 plus. So, what? The excitation or de-excitation is forbidden. The excitation and de-excitation directly is forbidden. From 0 plus to 0 plus it is not possible, right. So, that also I will discuss in due course. So, Hoyle has suggested that alpha plus beryllium 8 occurs through a resonant mechanism. And one more calculation you have to see. See, like for alpha plus alpha we have seen the gamma energy. Similarly, for alpha plus beryllium, if you see, Hoyle has predicted that somewhere around 230 keV, which is the centroid of the gamma peak for alpha plus beryllium, there should be an excited state in the carbon 12. I repeat, somewhere around the alpha plus beryllium 8 threshold, that is 7.366, and gamma peak centroid is about 230 to 280 keV. If you add these two, at that particular energy, there should be an excited state in carbon 12, and you can easily calculate and verify that it is about 280 keV. All right. Now, once it is known that the reaction is charged particle induced resonant reaction, let us go ahead with the reaction rate formalism, and you know how to find out how to understand the reaction rate formalism for the resonant reactions. Sigma V is proportional to strength of the resonance and exponential factor, where ER is your Hoyle state 7.644 MeV. And you know how to find out the strength of the resonance? It is the product of the partial widths, here in this case alpha particle threshold and radiative process, what is its partial width, okay, and then total partial width. So, with this we can find out the strength of the resonance, and here this partial width corresponding to the radiative decay is sum of partial width corresponding to the gamma emission and partial width corresponding to the positron electron pair emission. Where from these things are happening? See, from this 7.644 MeV Hoyle state to the ground state, gammas are emitted in cascade from 7.644 to 4.4 MeV, that is first excited state, and then from 4.4 MeV to ground state, 2 gammas are emitted. This is one way, because direct transition is not possible because of 0 plus to 0 plus transition is forbidden, isn't it? Second possibility is that 7.644 MeV energy can be converted into electron positron pair also. So, we need to consider the partial widths corresponding to these two processes. So, what is the total width? It is the sum of alpha particle width and width corresponding to gamma decay, width corresponding to positron electron pair. All right. Now, how to express the rate with which this triple alpha process is taking place? See, when I say triple alpha is taking place, it is not a single step, okay. As I told earlier, it is a double step process, it is a double step. So, what is the number density of beryllium 8, number density of alpha, and per pair what is the reaction rate? So, this is how we evaluate the reaction rate when we consider the triple alpha process. So, coming back to this equilibrium phenomena, we can express like alpha plus alpha is giving us to beryllium 8 and going back to alpha plus alpha. At the same time, there is a possibility that alpha plus beryllium gives rise to second excited state of carbon 12, that is 7.64 MeV. So, in a single notation we can do like this, like triple alpha and carbon 12 excited state. There is an equilibrium between carbon 12 excited state and also 3 alpha, because there is always a possibility that the excited state of carbon 12 can quickly go back to 3 alpha particles also, that also is possible, and after a certain stage we can expect some kind of equilibrium. All right. If it does not go back to 3 alpha, what will happen? I mean, when I say carbon 12, it is in the oil state. If it does not go back to 3 alpha particles, what will happen? It goes to the carbon 12 ground state, either by emitting 2 gammas from oil state to first exit state and then first exited state to the ground state, or it can emit electron and positron pair. All right. Now, here in principle there is a leakage in this equilibrium, there is a small leakage. What is that leakage? As I said, electromagnetic decay. This is happening when carbon 12 excited state and 3 alpha are trying to achieve the equilibrium. So, this electromagnetic decay is becoming the reason for the leakage. Fortunately, this is extremely small, like 1 out of 2500. So, we can always confidently say that the equilibrium can be reached. Now, combining this with the stellar rate equation and Saha equation, we can find out the expression for R 3 alpha, that is triple alpha reaction rate, triple alpha reaction rate. Now, what are the measurable quantities here? You have to find out Q value, you have to find out strength of the resonance, you have to find out the strength of the resonance. How to find out Q value? Take the mass of the carbon 12 in the excited state and take the masses of 3 alpha particles, take the difference and multiply with C square, you will get Q value. Now, there is a challenging part. One question I have posed in the first slide. Is it possible to perform this reaction in the laboratory? How can you perform the reaction between alpha and beryllium 8? Alpha and beryllium 8. Maybe you can form alpha plus alpha, but what about alpha plus beryllium 8? What is the problem? See, as I have told you already, beryllium 8 lifetime is 10 to the power of minus 16 seconds. So, because of this extremely small lifetime, it is impossible to prepare the target of beryllium 8. And when you cannot prepare beryllium 8 target, how can you carry out alpha plus beryllium 8? So, there is a challenge and there is no way to prepare beryllium 8 target. So, not only this, there is another challenge. What is that? Even when alpha plus beryllium 8 is we are able to do the reaction, the transition is forbidden, 0 plus to 0 plus. So, because of this experimental challenges, it is not possible to carry out alpha plus beryllium 8 reaction. Okay? So, we have to go for indirect measurements, we have to go for indirect measurements. One example is inelastic scattering, inelastic scattering. So, like shown here, see here carbon 12 you can take the target and take the proton beam. What energy you take you can easily calculate, because in whichever energy range you are interested for understanding the nuclear astrophysics process, that energy you can consider, and you consider the inelastic scattering of this proton. So, it is P prime, all right, and because of the inelastic scattering, carbon 12 gets excited to various states, of course, why not only to the Hoyle state, that is second excited state, but it also gets excited to the Hoyle state C12 star star. What will happen? This carbon 12 star star, that is Hoyle state, will disintegrate into 3 alpha particles. You detect those 3 alpha particles, you detect those 3 alpha particles using charged particle detectors like silicon barrier, sulfase barrier detectors, or you can use cesium iodide charged particle detectors. So, take a set of charged particle detectors and measure 3 alpha particles in coincidence. Their count rate will help you in finding out the cross section of this triple alpha process. So, this table shows you measurements performed by various researchers across the world, how the excitation energy can be measured, and finally, the Q value is coming out to be like 379.38 MeV. All right. There is another technique to understand this triple alpha process and to measure the cross section of triple alpha process, and that is implantation of boron 12 within a solid state counter. And when you implant boron 12 within the solid state counter, there will be a breakup of boron 12 into 3 alpha particles, and these 3 alpha particles can be measured using detectors, and one can find out the cross section of triple alpha process. And to conclude today's lecture, let me give you some number regarding the relation between energy produced in triple alpha process and the temperature of the star. The relation goes like this. It is proportional to 10 to the power of 41. So, you can imagine the sensitivity of energy production with respect to the temperature, sensitivity of the energy production with respect to the temperature. So, in a minute let me conclude today's lecture. So, we have seen how super red giant stars are formed. See, because carbon 12 cannot be formed in the early universe, because if it was formed in the early universe, we cannot explain the observed abundance. So, it has to happen within the star, and if it has to happen within the star, you have to address how stability gaps are filled, stability gaps are bridged. And the only way for this to happen, as suggested by Salpeter, is it is a two-step process. Assume that alpha plus alpha gives rise to beryllium 8 and beryllium 8 is reacting with alpha. But the problem is beryllium 8 is extremely short lived, it goes back to 2 alpha particles, but there is a possibility for beryllium 8 to capture the alpha particle to form the carbon 12. This is the contribution of Salpeter, and the contribution of Hoyle is suggesting that it is a resonant mechanism through which the excited state of carbon 12 is just higher than the alpha plus beryllium threshold around 280 keV, that you can calculate from the centroid of the gamma peak calculation, and because of that there is a formation of carbon 12. So, without Hoyle state carbon 12 cannot exist, and even only if we assume that this is happening through the resonance mechanism, then observed abundance can be explained, otherwise it is not possible. And later experimentally it was confirmed by many people across the world, okay. And experimentally it is very challenging to do these experiments because of the impossibility to prepare beryllium 8 target and the forbidden transition between Hoyle state to ground state, direct transition by gamma rays. So, one has to go for the indirect measurements like proton inelastic scattering induced by low energy protons. Thank you very much. Next lecture we will understand the survival of carbon 12. In today's lecture we have seen creation of carbon 12. In next lecture we will understand how carbon 12 survives in the helium burning phase. Okay? Thank you very much.